In this video, we will introduce the concept of the derivative. But first, let's recall an important fact that we've seen in previous videos. The slope of a tangent line to a curve at a point and an instantaneous velocity are both calculated in the same exact way. And the reason is, they both represent what we might think of as being just an instantaneous rate of change, something which from now on we will call a derivative. So the derivative of a function f is going to end up being another function denoted by f, and then we pronounce it f prime, and it is defined by the following limit. And this should look very familiar. The only difference between this limit and the previous limits we've evaluated is that instead of having a specific number, we just have a variable x, because we think of this as being the function f prime of x. And wherever this limit exists, we say that f is differentiable. A few observations. Finding a derivative is called differentiation of a function. And making the connection back to what we've previously seen, the value of a derivative at a point is the slope of the tangent line to the graph of the function at that point. This will be a very common thing for us to use later on when we're asked to find the equation of a tangent line. To find the equation of the tangent line, we need to find the derivative at the point, which will play the role of the slope. So let's investigate a few examples. Let's find the derivative of the function f of x equals 3x minus 6. So using the formula that we have from the previous slide, f prime of x is equal to the limit as h approaches 0 of the quantity f of x plus h minus f of x all over h. Now, a bit of terminology. This quantity that we are taking the limit of is something that we encountered previously. We refer to this as the difference quotient. So the first step towards evaluating this limit is to take care of the function evaluation. So every x in that function needs to be replaced with an x plus h. So this becomes the limit as h approaches 0 of 3 times the quantity x plus h minus 6, and this will be f of x plus h. Then we need to subtract away from this the function f of x. And this is all divided by h. Now, a spot where we need to be very careful in terms of the algebra involved is that when you're subtracting away the function, the minus sign out front needs to be distributed through so that it hits each term. So simplifying across the numerator, we'll have 3x plus 3h minus 6. And with the minus sign distributing through, we have minus 3x minus a minus, so plus 6. And some very nice cancellations occur. Minus 6 plus 6, minus 3x plus 3x. So what we are really left with in the top is the limit as h approaches 0 of 3h over h. The h's cancel, and this is really the ideal situation. You're left with just the limit of a constant, and the limit of a constant is always that constant. So what we have found is that the derivative, f prime of x, is defined to be just the value 3. So another similar example that uses definition of the derivative to find the derivative of the function 1 over x. So by definition, that derivative, f prime x, will be the limit as h approaches 0 of f of x plus h minus f of x all over h. And once again, the first thing we need to do is take care of this function evaluation. We need to go ahead and wherever we see an x in the function f of x, replace that x with with an x plus h. So this will become the limit as h approaches 0, and the function evaluation f of x plus h is 1 over x plus h. and we're subtracting away the function f. So we would like to simply plug in h equals 0, but unfortunately we cannot do that. It would give us an undefined quantity. So instead we need to algebraically manipulate. And really the only algebraic simplification we could note here is to combine fractions in the top. So to get that common denominator, we multiply the first fraction by, x over x, and we multiply the second fraction by x plus h over x plus h. Doing so is going to create a common denominator in the top, x over x plus h. And on top of that x over x plus h, we're going to have an x from the first fraction, and we're subtracting away from that an x plus h with the second. So the minus sign does need to distribute through. When it does, we'll have an x minus x, but we are also going to be left with a minus h. And once again, when we have a fraction divided by a quantity, we can simply take that quantity and move it up into the denominator. So our new denominator will be x over x plus h times h. The h in the top and the bottom will cancel. So that leaves us with just a minus 1 in the top, and the bottom is x over x plus h. And what we now have is a rational function in terms of h, so we can use the substitution property. That is, we can simply plug in h equals 0. So minus 1 over x times x. So minus 1 over x squared. So what this tells us is that the derivative we are hoping to calculate, f prime x, is the function minus 1 over x squared.